What up, what up? I'm the math teacher Goat, and today we're going to go over the very first section in AP Precalculus Change in Tandem. I'm going to go over every single section as AP Classroom describes, and basically the notes that you're going to see today, the lesson that you're getting is the exact same lesson and notes that I would give my own students. So in fact, if you just want to feel like you're sitting in a chair in my classroom, just download the notes in the description, print them out, follow along. Okay, so section 1.1, change in tandem. Without further ado, let's get started. Look at that graph. Isn't it neat? Wouldn't you think my graph is complete? Little Mermaid. Verbally describe where the x values are increasing and where the x values are decreasing. Be specific! Exclamation mark. All right, so we have this little piecewise thingy looking thing, and we're supposed to describe where it's increasing and decreasing. So I'm going to use good old notation, and I'm going to say, like good old regular, what's it called? Inequality notation. Wow, that took me a while. And I'm just going to say it looks like between 0 and 5. So I'll include 0. I don't know if 5 is going to be included, so I won't. I'm doing neither. Okay, I'm neither increasing nor am I decreasing. It's a nice flat surface. It's like a zero slope. So I'm going to say neither for that one, right? Now it looks like from 5 on to 8. So I will say 5 but not include it because I can't prove anything. And I will say 8 but not include that because I can't prove anything. It looks like we're increasing, okay? Increasing. Monsters Inc. So I'm going to write out increasing for that one. Monsters Inc. because they just put ink there. Now here between, what is that, 8 and 10? Definitely not including 8 and definitely not including 10. I am decreasing. Okay? Capiche? This is where you would say, if you were in my classroom, you would say capiche back. So basically, okay, the x values are increasing between 5 and 8, decreasing between 8 and 10 because, you know, positive slope and then negative slope. And since you're a zero slope, it's doing neither between 0 and 5. So that's my little warm-up, my little amuse-bouche, if you call it, to this lesson. A Ferris wheel spins at the same speed while it's in use. The maximum height of a rider is 95 feet and the minimum is 5 feet. The Ferris wheel rotates every 30 seconds. Sketch a graph relating height y to time x. All right, so we've got our height, which is y, height. And we've got our time, which is x, time. Now I'm only going to put the important things that I need. First things first, the maximum height is 95, so I'll put 95 right there. And the minimum height is 5. Okay? Does it say where we start out? No, so it doesn't really matter. But what's going to happen is you're going to start at 5 and you're going to increase in height, peak out at 95, decrease in height. Increase in height, decrease in height. So we start at 5, we increase in height, hit 95, and then decrease in height. So let's do it again because, you know, you're going to go more than around than once. So increase in height, hit your peak, decrease in height. Wow, that looks awful. But then you would do it again, and have this wave-like graph that happens. Now, I labeled my y values. What am I labeling my x values? Well, I start at 0, and every 30 seconds this process repeats. So that should be 60, not 30. Right, like so. All right, so you're going to get this wave thing. If I knew how to draw, you would get this wave thing that would just go up and down and up and down and up and down and repeat every 90, every 120, so on and so forth. Okay, this is going to become a theme, a huge theme in what we're dealing with. But what we see here is this change in waviness where you have this curve going up and down. Everything happens in waves, you'll see in algebra, or not algebra, pre-calculus. So that's very exciting. Now, some of the stuff that we're going to see to begin Precalculus is just kind of like stuff you already know. Like function notation, you should already know. Function means f of x, right? F of x is going to be your output value, your dependent value, what you get when you plug in some x value, which is your input or your independent variable. Again, we read it as f of x. Often we'll use g of x, maybe h of x, right? But if I give you a function, and in this case, I'm giving you the function 2x plus 7, right? And let me just demonstrate one of these, because why not? If I wanted to find f of 1 for 2x plus 7, you would replace every x with parentheses 1, plug it in, do some math. So 2 times 1 plus 7 is going to be 2 plus 7, which is 9. So at the end of the day, we could say that f of 1 is 9, and that's what we get here. F of 2, plug it in, 4 plus 7 is 11. F of 3, plug it in, 6 plus 7 is 13. F of 4, plug it in, 8 plus 7 is 15, so on and so forth. And you have a pattern being built that is linear in this case because that is a linear function. Okay? Okay, so page 1 complete. Now, let's talk a little bit about the independent and the dependent variables. The nice thing about this is you won't have to be so wordy in the future, but you might be asked what an independent variable versus a dependent variable is. In this problem, we have w of x is a function where w is the amount of water in a pool measured in gallons and x is the length of the pool. Okay, so it's asking here, what is the independent variable? The independent variable is the x value. Okay, so in this case, what does the independent variable represent? Well, x is the length of the pool. So in this case, the simple answer is the length of the pool. So similarly but different, the dependent variable is going to be your W, and W is the amount of water in the pool measured in gallons. So we'll just say the amount of water. Okay, so that is, again, just a little bit of review between the independent and dependent variables, stuff that you learned back in Algebra 1, Algebra 2. We're just bringing it back because, we might use those words from time to time. Now, an increasing function is as x values increase, the y, or we can call them f of x values, also increase. Okay, now 3 pictures because it could look like so many different things, but these are the common ones. Just a nice straight line going up and to the right. You may remember from Algebra 2 exponential functions looking something like this, or you might remember from Algebra 2 logarithmic functions looking something like that. Okay, so if the y values increase as the x values increase, you have yourself an increasing function. An increasing function. Now, in the next couple lessons, we will talk about increasing rates of change. In this case, we're just talking about increasing function, and that is basically as x go up, y go up. Decreasing function, as x go up, y go down. Okay, so the y or f of x values decrease. So, basic picture, go down and to the right. Maybe you have something that looks like this that starts to level off, right? Something that looks a little bit like that. Or maybe you have something that just super tanks, like this. Okay? So that is our decreasing function. Again, listen to my words, decreasing function. In the next couple days, we're going to talk, next couple lessons, we're going to talk about rates of change. Let's make sure that we're not getting things backwards. Let function f be increasing or decreasing, but not both. State whether the function is increasing or decreasing on the interval and justify. So what we're seeing here is the x values are increasing. And that will happen basically all the time unless the graph is supposed to be out of order on purpose. The f of x values are also increasing. So what we have here is an increasing function, and the way we would justify that is as the x values increase, the f of x values also increase. Bada bing, bada bang, bada boom. Halfway through. All right. So you will see that with my notes, what I do is I kind of give you a lesson, and then at the end we start doing some practice problems. So this is the lesson, and then in the next page we will do our practice problems, and then we'll be done. Zeros of a function. What are the zeros of a function? Well, the zeros of a function is where my graph crosses the x-axis. And in a function, it could happen once, it could happen never, and it could happen multiple times. If you're looking down here, you're going to see it happen multiple times. Okay, a y-intercept is where my graph crosses the y-axis, hence the name. Zeros of a function can also be called x-intercepts. They can also be called roots. They can also be called solutions. Y-intercepts are just called y-intercepts. So draw the zeros and the y-intercepts. Well, here's a 0, here's a 0, and here's a 0. 0 number 1, 0 number 2, 0 number 3, 0. With the parentheses because I want to. Here's my y-intercept. Easy peasy lemon squeezy. Now, this is what I've been warning you about a couple times. Concave up. By definition, concave up, graphically, we'll look at it first. Graphically, concave up is going to look like this. Okay, that is concave up. By definition, concave up is your rate of change is increasing. Now, let's remember some of our words from back in the day. Okay, rate of change is a fancy word for slope. So if I were to look at this guy and put a couple dots here, I'll put a dot here, I'll put a dot here, I'll put a dot here, and I'll put a dot here. If I were to be like, let's draw where we think a slope would be on this guy, we're going to pretend that basically we're on a roller coaster and the roller coaster car represents our slope at the moment. So right now at that moment at the very left we have a negative slope. But as the car of the roller coaster starts hitting the bottom of the hill, it starts to flatten out. So the negative ain't so negative anymore. Then this next dot, we have a small positive slope, so the roller coaster car looks like that. And then as we move on, the roller coaster car is moving upwards. So my rate of change as I move to the left to the right, my slope is increasing. I go from a negative, small positive, big positive. My rate of change is increasing if something is concave up. And again, what that looks like is a bowl or something like that. Now, concave down is my rate of change is decreasing. My rate of change is decreasing. What that looks like graphically is an upside down bowl or an upside down parabola looking thing. But similarly, I can pick a couple dots on here. Here's a dot, here's a dot, here's a dot. And if this was a roller coaster, I start out all the way to the left with a nice positive 1. Once I hit my very tippy top, I have a 0 slope. And once I make my way down, I have a negative slope. So my slope goes from increasing to decreasing, or rather from positive to negative, which means my rate of change, my slope is always decreasing. So there's a huge difference between an increasing function versus an increasing rate of change. Okay, this is an increasing function. This is an increasing rate of change. My increasing rate of change is actually decreasing and then increasing. So there's a huge difference between the two. Make sure you understand that. What's very important is what an inflection point is. An inflection point is a change in concavity. Concavity is just fancy talk for concave up versus concave down. Or concavity could also mean if you're an ex-con and you need to get some dental work. concavity? Oh, that should be my side gig. I should get my dental license and then work only with ex-cons and call it concavity. Anyway, what that might look like as a picture is if I give you a picture that looks like this, right? I start out by looking at concave up, and then all of a sudden, right around here, it stops being concave up and starts being concave down. And then right around here, it stops being concave down and starts being concave up again. So these would be the inflection points, the areas where it appears that it stops being concave up and starts being concave down, and vice versa. Okay? So those are my inflection points, also known as points of inflection. All right, interval notation. Now you saw at the very beginning I used something like this, right? I used something like, what was it? 0 is less than x is less than 5. And that was to say that actually I think I used that. That was to say that we are going to include 0, and I care about the x values between 0 and 5, including 0 but not 5. Well, now we're going to do the same type of thing, but we are going to use interval notation almost exclusively in pre-calculus. You'll see this some percent of the time, but this a lot more percent of the time. What a parentheses means, okay, is between -5 and 6 dot dot dot. But when it's a parentheses, you don't include -5, but you do including 6. So the bracket means you are including it, and the parentheses means you don't. So you would write this out as -5 is less than but not including x, which is less than but is including 6. Okay, so without having to write this out, you would include 5, but it doesn't even make sense to include infinity. You never put a bracket around infinity. You only put parentheses around infinity. So we would write this out two ways, actually. We could write this out as 5 is less than or equal to 6, which is less than infinity. But I think most people would prefer to write it out as everything greater than or equal to 5, which includes infinity. Okay, so we are going to use interval notation. Parentheses means you include the number. Parentheses means you don't include the number. Bracket means you do include the number. Bracket means you include the number. Parentheses means you don't. Now, if we're dealing with 2 or more intervals, we're going to use this thing called union. For example, if I have intervals 0, 5, including 5, and also 7 to infinity, I'm going to put this U-shaped thing, which means union. So if I have 2 or more intervals, we are going to use this union symbol instead of the word and. Why? Because it's faster. And if I have 3 intervals, then I'm going to have a couple unions in between. Simple. Now let's do some, examples based off of what we learned today. See if we can put all of this together. Let's look at some examples. Use the graph of f below to answer the following questions. When is the graph concave up? All right. So basically I have all of these letters. I have G, H, I, J, K, L, M, and then I have my infinities. It looks like it's going to be concave up from negative infinity all the way to I. So negative infinity all the way to I is where it's going to be concave up. That looks like an inflection point, and so you know what? This would probably be an inflection point too. So from negative infinity all the way to I, and we're not going to include it because at the point of inflection, it's neither concave up nor concave down. So when you're dealing with concavity and it asks you these questions, you're never going to include your inflection point. Don't include your inflection point. However, that's not the only concave up. It's also concave up from k to positive infinity. So we will say union k to positive infinity. Where is this concave down? From I to k. Or as the kids say, ick. Don't include I or k because you're not going to include your points of inflection as part of concavity. Find the zeros of the function. All right. Well, my zeros are where my graph crosses the x-axis, and that happens at G and M. So I will say x equals G and M. Find the y-intercept of the function. Well, the y-intercept of the function occurs as this guy called a, so we will say f of 0, or y, equals a. Where is the graph increasing? Now keep in mind, when the graph is increasing, that's not the same as concave up, concave down. Concave up is where the rate of change is increasing. Concave down is where the rate of change is decreasing. Okay, where the graph is increasing is any time you're going up and to the right. And that happens from H to J, you are increasing, and then all of a sudden decreasing, and from L to forever. So we will say the graph is increasing from H to J. Don't include either of those, because at H, you're doing neither. You're at a zero slope. Okay? So H to J, union, and then L to infinity. Last but not least, we have ourselves, where is this decreasing? And this is decreasing from negative infinity to H, and then picks up again from J to L. So negative infinity to H, union J to L. All right. Okay. Let the function f be defined as a function that is always decreasing. The table shows values for the function f at selected values of x. So we're going from -5 to -2 to 0 to 3 to 4. There's no pattern. Which of the following represents all the possible values of a? Well, if this is always decreasing, right? If this is always decreasing, that means these numbers will always be decreasing. So a lives sandwiched here between 4 and -2, which means a has to be in between 4 and -2. Now, we're not going to look for patterns because we don't know what the graph looks like. We just know that a cannot be 4 and a cannot be -2, but you know what? It could be everything in between. Now, here we are looking at this, and this is inappropriate math work. This doesn't make sense. Because you wouldn't write out something as 4 is less than a, which is less than -2. Last time I checked, 4 is not less than -2, so that's bad grammar. So we actually have to flip this around. -2 is less than a, which is less than 4. So that gives me the answer of D. Okay? Okay. A couple more. 2 more. The function g of x is defined on the interval 0, 8. Based on the values in the table, where is the function increasing? All right, so my x values are going up by 1 every single time, so I need to find out where g of x is also going up. So you start out right away going up, so we're adding 1, adding 1, adding 1, all of a sudden we stop and we go down. So here we are increasing. Here is an increase. So we go from -5 to -6, but from -6 to -3, so we go from here and we start increasing again. But then here we go from -3 to -4, so we start decreasing. So we're going up, go down. Okay, go down, and then all of a sudden go up again, and then go down again. So our intervals are going to be between 0 and 2, union 4 and 6. And that's where we're increasing. So again, let's just wrap this up by answering this question. Okay, rate of change means slope. Circle the word that completes the statement. The rate of change at -1.56, 0.313 is doing what? Well, what it wants me to do is it wants me to put my slope right there like we did right there. Now, my rate of change, okay, my rate of change at that point is positive. Ooh. Now, it's not increasing because I don't care what's happening over the span of time. I care about what's happening at that point. And at that point, my rate of change is positive because it represents a positive slope. So that's 1.1. What I suggest you do is you hit that like and subscribe button, please, please, please. Make a comment if you want, say how awesome I am. But when you're done, go to my YouTube and oh my gosh, search my random videos. Just type out, right down here, type out section 1.1 example, and you will get a couple problems that will help reinforce what you learned today. All right, so I appreciate you guys watching. Thanks for watching. I love you all. Continue watching. Don't forget to download these notes and copy them and do everything I need you to do to help this YouTube grow. Thanks for watching. Love you. Bye.